Okay, so in this video we're going to talk about antiderivatives. So we'll start with the definition. The antiderivative of a function undoes the derivative on that function. So schematically, what an antiderivative is if a derivative takes you from f to f prime, this is a derivative. An antiderivative takes you back. Antiderivative goes the reverse direction. And we're going to use some notation to denote this antiderivative. We'll use indefinite integral notation. We typically include a constant c. Okay, so let me update my diagram here. So derivative takes you from f to f prime. Our Leibniz notation here is derivative of f. And then our integral notation is for going backwards. So we're going to look at the integral of f prime is going to be f. And when we go back, we typically include a c. So we'll write f plus c instead of just f. All right, let's look at a few examples. So let's find the antiderivative of each function. We'll look at 4 functions. We'll look at the f prime of x is 2x. The g prime of x is 3x squared. And then h prime of x is just x squared. And then last but not least, L prime of x is 1 over x squared. So doing the antiderivative, we think about reversing the derivative. So we ask ourselves, what function has a derivative of 2x? And we've worked enough with polynomials to know that that function is x squared. We're going to include a plus c here because when you take the derivative of c, you get 0. So the derivative of any function, x squared plus c, is going to be 2x. Okay, so this is our antiderivative. All right, g of x, if g prime of x is 3x squared, g of x is going to be x cubed. If you take the derivative of x cubed, you get 3x squared. Again, we'll include a plus c. Now, the antiderivative of x squared is not so straightforward because there isn't that 3 in front. So we have to think about what function has a derivative of just x squared. No 3x squared, just x squared. And if you think about this long enough, you'll find that that function is 1/3 x cubed. And the reason it's 1/3 x cubed is when that 3 comes down, it needs to disappear. So we need a 1/3 coefficient to cancel the 3. And these first 3 antiderivatives suggest for us a rule. Let me write it over here. I'm going to call this rule the reverse power rule. And it goes like this. The antiderivative of x to the n is x to the n plus 1 over n plus 1. You can check this rule by differentiating the right-hand side and seeing that we get our original expression. So the c will be 0, and the dividing by n plus 1 is just like multiplying by 1 over n plus 1. So we can skip over that. And we'll get 1 over n plus 1 times n plus 1, the power comes down, times x to the n. And those n plus 1's cancel, and we're left with x to the n. So this rule is correct. Let me put a box around it. It's a very important rule. And this rule allows us to antiderive this last function up here, this L prime of x. Okay, so first what we're going to do is we're going to write this L prime of x as x to the negative 2. And then we'll use this reverse power rule. We'll say that L of x is going to be x to the negative 2 plus 1 all over negative 2 plus 1 plus c, which simplifies to x to the negative 1 over negative 1 plus c, or negative 1 over x plus c. Okay, let's learn a couple more rules for antiderivatives. Okay, so the first rule is the sum or difference rule. It says the integral or the antiderivative of f of x plus or minus g of x is the antiderivative of f of x plus or minus the antiderivative of g of x. And then the second rule says if you take the antiderivative of c times a function, c times f of x, that's the same as c times the antiderivative of f of x. Okay, so let's look at a couple examples that use these rules. So let's evaluate the following indefinite integral, or in other words, compute the antiderivative of this function. So we're first going to apply the first rule here, the sum rule. We're going to write this as the antiderivative of x cubed plus the antiderivative of 4x squared. And then we can take the coefficient rule, the second rule, and rewrite that second integral as 4 times the integral of x squared dx. And then we just apply the power rule twice, the reverse power rule twice. We'll get x to the 4th over 4 for the first, and x cubed over 3 for the second, leaving that 4 coefficient and adding a plus c. And we can rewrite this slightly like so, make it a little cleaner, and we have our answer. Let's look at another example. So in this example, we're going to evaluate the integral of x cubed plus 1 all over x cubed. So we see we have a quotient here, and there's no rule for antideriving a quotient, so we need to rewrite this. And so what we're going to do is we're going to rewrite this as a sum. The way we do that is we rewrite this as x cubed over x cubed plus 1 over x cubed. Okay, this is just a property of fractions. A plus b over c is the same as a over c plus b over c. It's a property of fractions. Typically, we're going the reverse direction here. We're creating a common denominator and adding. But in this problem, we want to reverse that direction, and we want to write it as two fractions. And then what we can do is we can use exponent rules to simplify, and we'll get 1 plus x to the negative 3. And then we can use the reverse power rule in each of these terms. So we'll first rewrite it as the integral of 1 and the integral of x to the negative 3. The antiderivative of 1 is x. You could think of that as x to the 0. You add 1 to 0, you get x to the 1 over 1. Or you can just think what function has a derivative of 1, and that is x. And then our second term will be x to the negative 2, adding 1 divided by negative 2, and then that plus c. And we can rewrite this slightly like so, if you don't like negative exponents, and you get this answer. All right, I hope you found this video useful.